First, let me introduce to you the spacetimes in general relativity, the Barnik quasi-local mass, and Barnik boundary data. In general relativity, we use spacetimes as mathematical models of gravitational systems in physics. A spacetime is a pair consisting of a smooth four-dimensional manifold V and a metric G, which has one negative and three positive eigenvalues in its signature. The simplest example of a spacetime is the Minkowski spacetime, where V is the Euclidean R4 space with Cartesian coordinate, and the metric G is the flat metric with a negative sign in the t direction. Here we call t as the time function of the spacetime. We can observe that any vector along the t direction has negative norm. Those are called time-like vectors. And if a vector is with positive norm, it's called space-like vectors. Like in this picture, we can decompose the spacetime as space and time. With the help of a time function, we can think of the spacetime as formed by a foliation of hypersurfaces, where along each hypersurface, the time t is constant. Every such hypersurface is a three-dimensional manifold. We name it as M. The ambient spacetime metric induces a remaining metric gamma on M and the extrinsic curvature tensor K on M. More precisely, K is the second fundamental form of the hypersurface, which measures how M is curved in the ambient space. Here, this triple M gamma K is called an initial dataset of the spacetime. An important portion of the research in general relativity is to study the mass of initial datasets. One of the most well-known notions of mass in general relativity is the ADM mass for asymptotically flat initial datasets. Here, an initial dataset is called asymptotically flat if M minus a compact subset D is diffeomorphic to R3 minus the unit ball. And we also require the metric gamma decay to the flat metric and the extrinsic curvature K decay to 0 at infinity. For such an initial dataset, we can measure its total mass using the ADM mass, which is defined as the norm of this 4-vector. Each component of the vector is defined as a flux integral at infinity. The ADM mass has been very well studied, and we have the well-known positive mass theorem. Meanwhile, most of the physical models are regions of finite extent, corresponding to initial dataset, where the manifold M is a compact 3-manifold. So we are very interested in the mass of compact initial datasets. However, in this case, there's no canonical method to measure the mass. In fact, to find a suitable quasi-local definition of mass for compact initial dataset is an important unsolved problem in classical general relativity. One of the most interesting notions of quasi-local mass is the Barnik quasi-local mass, defined by a quasi-localization method of the ADM mass. Given a compact initial dataset M0, G0, K0, where M0 is a compact manifold with non-empty boundary, denoted as sigma here, we can first extend this to a complete asymptotically flat initial dataset, where we use M gamma K to denote the extension. Then we can measure the ADM mass of the extension, and after that, we take the infimum ADM mass over all possible extensions. That infimum is then defined as the Barnik quasi-local mass of the compact initial dataset. Here, when we construct extensions for the compact set, we need to make sure that the geometry is consistent across the boundary, in the way that a collection of geometric boundary data along sigma, which is induced from the exterior region, is equal to that data induced from the interior region. Mathematically, that's the Barnik boundary conditions, which requires the Barnik data of the extension initial data set is equal to the Barnik data of the compact initial data set. Here, the Barnik data of an initial data set consists of the induced metric on the boundary, the mean curvature of the boundary, the restricted trace of the tensor K along the boundary, and the tensor K contracted with the unit normal vector along the boundary. There are some other technical assumptions for extensions M gamma K, such as the non-horizon condition and the dominant energy condition. With all those conditions satisfied, we call such an extension as an admissible initial data set, or an admissible extension. For such a construction, it is conjectured by Barnik that for arbitrary compact initial data set, there is an admissible asymptotically flat initial data set realizing the infimum ADM mass in the definition here. Moreover, the initial data set which realizes the infimum must be a stationary vacuum initial data set. In other words, it means that this M gamma K can be embedded as an initial data set into a space-time where the space-time metric satisfies the stationary vacuum equations. So next, let me introduce to you the stationary vacuum Einstein equations. In general relativity, a space-time must satisfy the Einstein equations, which require the Ricci tensor of the metric minus 1/2 the scalar curvature of the metric times the metric tensor should equal to a tensor T. Here, T is called the stress energy tensor. It is determined by the physical matter fields of the space-time. In the case where T equals to 0, this equation will be called the vacuum Einstein equation, and the vacuum equation is equivalent to the Ricci flat equation. Such a spacetime will be called a vacuum spacetime. Furthermore, a spacetime is called a stationary spacetime if there exists a time-like vector field dt so that the Lie derivative of the spacetime metric with respect to dt is equal to 0. In other words, we can think of t as a time function of the spacetime, and this equation is equivalent to that the metric is invariant under time translation. In this case, the spacetime metric G is uniquely determined by its information when t equal to 0. That is essentially the initial data set induced on this hypersurface. Now, a stationary vacuum spacetime is a spacetime which is both stationary and vacuum, that is Ricci flat. If we choose a special coordinate for the spacetime, which is called the harmonic chart, we can write down the stationary vacuum equations as a system of partial differential equations, and this is the leading order part of the PDE. Here, the operator colored in blue is essentially the Laplace operator with respect to the remaining metric induced on the t equal to 0 hypersurface. So the stationary vacuum equations essentially form an elliptic system. Recall that the Barnik conjecture says the extension realizing the infimum ADM mass must be a stationary vacuum initial data set, which means the extension can be embedded into a stationary vacuum spacetime as an initial data set. And meanwhile, the extension should satisfy the Barnik boundary conditions. This motivates us to consider the PDE system of the stationary vacuum equations coupled with the Barnik boundary conditions, which give rise to the following boundary value problem. Let M be a manifold diffeomorphic to R3 minus the unit ball, whose boundary is denoted as sigma. We consider stationary spacetime metric G and spacetime manifold V, which is the product manifold between M and the time interval 0 to infinity. We want to solve for G so that it satisfies the stationary vacuum equation on M and satisfies the Barnik boundary condition on sigma. Here, this M gamma K is the initial data set induced from G on the initial surface t equal to 0. The Barnik boundary condition requires the Barnik data of that initial data set equal to some prescribed data B0. Now, using the system of this boundary value problem, we can interpret the Barnik conjecture into two parts. The first part is that for fixed data B0, if the infimum ADM mass taken over all its extensions is realized by some initial data set, then that initial data set can be embedded in a stationary spacetime where the metric solves this system here. And the second part is that given prescribed Barnik data B0, there exists a solution to this system. To solve those open problems, the first step is to show that the Barnik boundary condition is elliptic. That is, this system is an elliptic boundary value problem. So next, we will talk about in detail how to prove ellipticity of this system. One of the most important parts in the discussion of ellipticity is the gauge modification. Here, we consider the vacuum equation for stationary metrics. In fact, this is a degenerate elliptic system. A basic observation is that if Vg is a stationary vacuum spacetime, then we can pull back the metric using any diffeomorphism C from V to V, and then the pullback metric will still be stationary vacuum. It means that the kernel of this equation is of infinite dimension, so it cannot be elliptic. However, we can modify the equation to be elliptic by adding a gauge term. Here, we change the Ricci flat equation to be Ricci tensor plus an extra term is equal to 0. Here, G is the unknown metric we want to solve for, and bar G is a fixed background metric, which is stationary vacuum. We use beta bar G on G to denote the vector field obtained by taking the Bianchi operator on G with respect to the background metric bar G. In detail, the vector field beta bar G of G is equal to minus divergence with respect to bar G on the metric G plus 1/2 d of the trace with respect to bar G on G. Then the star of this vector field is in detail given by the Lie derivative, which is equal to 1/2 the Lie derivative of the vector field on the unknown metric G. We also add the Dirichlet boundary condition that this vector field is equal to 0 on the boundary. After the modification, we can check the symbol of this bulk equation and verify that it becomes an elliptic equation for the metric G. Moreover, we need to make sure that solutions to the modified system are still stationary vacuum. To do so, we can use the Bianchi identity for the Ricci tensor. It is a basic fact that if we take Bianchi operator with respect to the metric G on the Ricci tensor of G, this is always equal to 0. Based on this fact, we can try to take Bianchi on the bulk equation. Now, for simplicity, Let's call this gauge vector field as the vector field Z. Then we can take Bianchi of the Ricci plus Bianchi del star, again with respect to G, on the vector field Z. This is equal to 0 based on the bulk equation here. Now, based on this fact, the first term here vanishes, so we obtain an equation for the vector field Z, which tells Bianchi del star Z is equal to 0 on the manifold M. Furthermore, we have this Dirichlet boundary condition, which tells Z is equal to 0 on the boundary sigma. So we obtain a boundary value problem for the gauge vector field Z. We can further show that this is elliptic, and also if metric G is nearby the background metric bar G, then this system has only trivial solution, which means Z must equal to 0 on manifold M. So now if Z is 0 from the bulk equation, this term vanishes, so we obtain Ricci of G is actually equal to 0. Therefore, we obtain the conclusion that near the background metric bar G, any metric satisfying the gauge modified system must also satisfy the original stationary vacuum equation. Conversely, we can show that if G is a solution to the original stationary vacuum equation, then we can pull back G via a diffeomorphism, so that the pullback metric is a solution to the gauge modified system. In other words, if we use S to denote the solution space of the original stationary vacuum equation, and use tilde S to denote the solution space of the gauge modified system, then tilde S is essentially the space S quotient by the diffeomorphism group of the space-time. So this gauge modification helps us to eliminate the infinitely many kernel elements which are generated by the diffeomorphisms of the space-time. Now, with this bulk equation being elliptic, we can add to it the Barnik boundary conditions. So we establish this boundary value problem where the bulk equation is the gauge modified Ricci flat equation, and the boundary conditions consist of the boundary condition for the gauge vector field and the Barnik boundary conditions which we introduced before. We would like this to be a well-posed elliptic boundary value problem. However, we can easily observe that there are 10 bulk equations but 11 boundary conditions. We can try to count the number of equations in this system in detail. Here, this is the Ricci tensor of a metric on a 4-dimensional manifold. So if we write down this in a coordinate chart, we have Ricci of the metric ij component, which can be understood as a 4x4 matrix. Therefore, we have 10 unknowns in this tensor, so this bulk equation gives rise to 10 equations on the manifold M. On the boundary conditions, this is the gauge vector field. It is a vector field in a 4-dimensional manifold. Therefore, it gives 4 boundary equations. The induced metric on the boundary surface sigma is a metric on a 2-dimensional manifold. So if we write it down in coordinate chart, this can be understood as a 2x2 symmetric matrix. So it has 3 unknowns, so this equation gives rise to 3 boundary equations. The mean curvature is a scalar field on the boundary, so this gives one equation on the boundary. Similarly, trace of a tensor is also a scalar field, so this gives rise to one equation on the boundary. This can be understood as a one form on the boundary surface, which is a two-dimensional manifold, so this gives rise to two boundary equations. Then if we add those up, we see that there are in total 11 boundary equations on sigma. The reason for this issue here is essentially that by adding this gauge modification to the system, we are considering two solutions, G1 and G2, as equivalent solutions to the static vacuum equations if G1 is equal to the pullback of G2 by a diffeomorphism psi from V to V, such that when restricted on the boundary surface sigma, psi is equal to the identity map of the boundary sigma. However, the Barnik boundary data of an initial data set is not always preserved under such diffeomorphisms of the space-time. In particular, they are not preserved under a time translation of a space-time, which equal to identity on the boundary, but does not have vanishing Neumann boundary condition. A key observation is that we have this transformation formula for the Barnik boundary data via a diffeomorphism of the space-time that is a time translation. Recall that we think of the space-time manifold as the product manifold between m and the time interval 0 to infinity. So if we use p to denote a general point in m and t to denote a time in the time interval, then we can use this pair pt to denote a general point in the space-time. Now we think of a general time translation map, which maps a pair pt to the new pair p and t minus f of p, where f is a function defined on the hypersurface M. Then under this time translation, the Barnik data of the original metric and that of the pullback of the metric are related by those formulas, which we see that the induced metric on the boundary surface sigma is preserved, but the mean curvature, restricted trace of the tensor K, and the connection one form on the surface sigma are all changed. Here, those coefficients A, B are scalar functions on sigma, and they are uniquely determined by the metric G and the Neumann data of this time translation function F. Now, based on this observation, we can set up the new boundary value problem where we change the Barnik boundary conditions to these new boundary conditions. Here, we recall the Barnik boundary data of the metric after certain time translation is equal to the prescribed data. This A and B are the scalar functions which we obtained from this transformation formula. We know that A, B are determined by the metric G and the Neumann data of certain time translation function. Therefore, we need to add a new variable to this system denoted by f here, and we understand the Dirichlet data of this function on the boundary manifold as the Neumann data of some time translation function. In other words, f is involved in the boundary equations via A and B. So here A is a scalar function determined by the metric G and the Dirichlet data of f, and B is also a scalar function determined by G and f on the boundary. We are quite free to choose the bulk equation for the function f, so we choose the simplest elliptic equation, which requires f to be harmonic on the manifold M. Now we can count the number of equations, so we have 11 bulk equations and also 11 boundary equations. Furthermore, we can calculate the symbol of the bulk equation and the boundary equations and verify that this is actually a well-defined elliptic boundary value problem. Along this path, we finally show that the Barnik boundary conditions are elliptic for the stationary vacuum Einstein equations, and the moduli space of asymptotically flat stationary vacuum spacetimes is an infinite-dimensional Banach manifold. Next, let's talk about the first part of the Barnik conjecture about the mass-minimizing extensions, which states that if an extension realizes the infimum ADM mass, then that must be a stationary vacuum initial data set. That part of the conjecture is first proved in the static case. Here we say a spacetime is static if there exists a time function t in the spacetime so that any time slice defined by t equal to constant in the spacetime is a space-like hypersurface with vanishing second fundamental form. In this case, the initial data set induced on each time slice of the spacetime is simply a Riemannian manifold. Then we can write down a copy of the definition of Barnik quasi-local mass, simplified in the case where the spacetime is static and the initial datasets are Riemannian manifolds. Suppose M0 gamma naught is a Riemannian manifold where M0 is compact manifold with non-empty boundary denoted as sigma. Then the Barnik quasi-local mass of this compact Riemannian manifold is defined as the infimum ADM mass taken over all its extensions. Here extensions are asymptotically flat Riemannian manifolds which satisfy the Barnik boundary conditions on sigma. And the Barnik boundary conditions are also simplified, which only require the induced metric and mean curvature of the extension is equal to that data induced from the compact Riemannian manifold. It has been proved by Anderson and Jerrigan that if an admissible asymptotically flat extension realizes the infimum ADM mass here, then that extension must be a static vacuum extension. We will introduce the detailed equation of static vacuum extension in the next section. Here, let's first talk about the conjecture about the mass minimizing extension in the general case. Recall that any spacetime must satisfy the Einstein equations. Because of this, any initial dataset embedded in a spacetime must satisfy the constraint equations, where on the left-hand side we have the curvature tensors, and on the right-hand side we have nu and g, which are uniquely determined by the stress-energy tensor T. The constraint equations are essentially obtained from the Gauss and Caudacy equations for hypersurfaces in differential geometry. Then inspired by the work of Anderson-Jerrigan for the static case, here we want to consider a special space of asymptotically flat initial datasets. Here we fix some data nu G and Barnik data B naught. Then this space, constraint space C, is defined as the space of all the asymptotically flat initial datasets which satisfy the constraint equations for the fixed nu and G, and which satisfy the Barnik boundary conditions for the fixed prescribed data B naught. Then we use the ellipticity result of the Barnik data to obtain that the constraint space C has the structure of a smooth infinite-dimensional Banach manifold. Since C consists of asymptotically flat initial data sets, we can evaluate the ADM mass of those initial data sets. It means that we can think of the ADM mass as a function which maps C to the real numbers R. It simply assigns each initial data set in C with its ADM mass. This is a well-defined function, and furthermore, we show that if an initial data set is a critical point of this ADM mass function on the constraint manifold C, which has positive mass, then it must admit a K-ling initial data, which is asymptotically time-like. This result tells us some geometric property that a mass-minimizing extension should satisfy. If we take a compact initial data set, which gives rise to a fixed Barnik data on the boundary, and then we consider all possible asymptotically flat extensions for that, and assume M gamma K is the initial data set which realizes the infimum ADM mass that is positive, then we can take the constraint U and J, which are satisfied by this M gamma K, and consider the constraint manifold C nu J be null. Then we know that because the ADM mass of this M gamma K is the infimum, this M gamma K must be a critical point of the ADM mass function on this manifold C. Then by this theorem, we know that such a mass-minimizing extension must admit a K-ling initial data. In fact, admitting a K-ling initial data is a necessary condition for an initial data set to be embedded in a stationary spacetime. We also refer to the work of Huang Li, where the authors prove that if an initial data set realizes the infimum ADM mass, then it must sit in a null-dust spacetime, and if the ADM mass is positive for this initial data set, then it must satisfy the vacuum constraint equations outside the compact subset. Next, let's talk about the second part of the Barnik conjecture, which states that for any prescribed Barnik data, there always exists a stationary vacuum extension. Actually, this conjecture is widely open, and so far, we only have known results in the static case. Here, we recall that if a spacetime is static, then the initial data sets are reduced to Riemannian manifold, and an extension which realizes the infimum ADM mass will be a Riemannian manifold that is static vacuum. Here we call a manifold as asymptotically flat and static vacuum if there is a potential function U on the manifold M, so that U decay to 1 at infinity, and meanwhile the metric gamma decay to the flat metric at infinity. Furthermore, this gamma U should satisfy this system called the static vacuum equations on the manifold M, which requires that U times Ricci tensor of the metric minus Hessian of the function U with respect to the metric should equal to 0. And furthermore, U should be a harmonic function with respect to the metric gamma. If we have a pair gamma U satisfying these static vacuum equations, then we can establish a spacetime metric G, which is equal to negative U square dt square plus gamma. This is a spacetime metric defined on the spacetime M product with the time interval 0 to infinity. then this spacetime will be a static vacuum spacetime. Well-known examples for exact solutions of these static vacuum equations are the Minkowski spacetime and the Schwarzschild spacetime. In the Minkowski spacetime, the gamma is the flat Euclidean metric and the potential function is the constant function 1. And in the Schwarzschild spacetime, gamma is the remaining metric in this part of the formula, and u is square root of this coefficient function here. Motivated by the Barnik conjecture, we would like to study the Barnik boundary value problem for static vacuum equations, where the bulk equations are the static vacuum equations and the Barnik boundary conditions are imposed on the boundary surface sigma. To get an example of a solution to this boundary value problem, we can think of the case where m is equal to R3 minus the unit ball. Then the boundary of M is the standard unit sphere. We can take the metric gamma as the flat metric and the potential function u as the constant function 1. Then this is the solution to the bulk equation, and on the boundary the induced metric on the standard unit sphere is of course the standard round metric, and the mean curvature of the standard unit sphere is equal to 2 everywhere. Therefore, we can think of this as the solution to this boundary value problem, where tau is equal to the standard round metric and phi is equal to the constant function 2. If we consider this boundary value problem with arbitrarily prescribed Barnik data tau and phi here, then in fact for a long time the only known existence results for this boundary value problem is that if the prescribed data is near the standard Barnik data on the unit sphere, then there always exists a solution to this boundary value problem. This result is first proved by Miao under a reflectional invariance condition for this Barnik data, and then proved by Anderson by removing that reflectional invariance condition. Motivated by this result, we would like to ask the following question. If we have a background Riemannian manifold which is asymptotically flat and static vacuum, where its Barnik data is the induced metric and mean curvature from the background Riemannian metric bar gamma, then if tau and phi is near the background Barnik data on sigma, does there exist an asymptotically flat static vacuum extension for tau and phi? In other words, we would like to ask if this tau and phi is a perturbation of the background Barnik data, then do we always have a solution to this boundary value problem? In a recent joint work with Lanshan Huang, we prove a sufficient condition for the existence of solutions to this system. We introduce a technical condition called static regular boundary, and we show that given a general background static vacuum triple, if its boundary is a static regular boundary, then for any prescribed data tau and phi, which are close to the background Barnik data, then there always exists a asymptotically flat static vacuum pair which solves this system with prescribed data tau and phi here. Moreover, this solution is also close to the background solution bar gamma bar u, and locally it is geometrically unique. Furthermore, we studied which surfaces can be static regular, and we showed that in a background static vacuum manifold, If we have a family of bounded open subset omega t, where t varies from negative delta to delta, and if the boundary of the omega t, denoted as sigma t here, form a smooth foliation of embedded hypersurfaces, so that the deformation vector field is always transverse to each hypersurface, then there must exist an open and dense subset of the time interval, so that for every t in that subset, sigma t must be a static regular boundary for the exterior manifold m minus omega t. It is also illustrated in this picture. If you have a family of surfaces sigma t in the background manifold M with the deformation vector field transverse to each hypersurface, then except for some discrete bad choice of the hypersurface, all the other hypersurfaces are static regular. Based on this result, we further use a dilation argument and show that any star-shaped surface in the dimension n Euclidean space is always static regular. And in an upcoming work, we will show that any sphere in the three-dimension Schwarzschild manifold is always static regular. That is the end of my talk. Thank you very much for watching this video.